Okay, now we're ready for the alternating series test. And so first let's just discuss what is an alternating series. Well, an alternating series is when the sign alternates between positive, negative, and so on. And so something like this, perhaps. What if we had like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. This would be an example of an alternating series. Okay. So this one, for instance, if you look at this, it's going plus, minus, plus, minus. That's an alternating series. But if we look at specifically at what this series is, this is something we've seen before. This is the alternating part, but if you ignore that, we're going 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. This is called the alternating harmonic series. 1 over n, from n is 1 to infinity, is the harmonic series, which we know it diverges. But if we put this condition, negative 1 to the n minus 1 or n plus 1, you could call it either one, this would describe the series, because if n is 1, 1 over 1 is 1, negative 1 to the 1 minus 1 is 0, that'd be a positive 1, plus the next term, 1 over 2, 2 minus 1 is 1, negative 1 to the 1 is a negative 1, 3, 1 over 3 is 1 over 3, and then 3 minus 1 is negative 1 squared, which is a positive 1, and so on. This is what this is describing right here. So we might wonder, like, hey, is this, even though it's known that the regular harmonic series, 1 over n, diverges, what about the alternating harmonic series? So we're going to have a look at that in a minute. There is a test we can use for alternating series called the alternating series test. Okay, and it says basically this: if you have an alternating series, and so this part right here is what makes it alternate. Negative 1 to a power changes that sign for us. If you have some alternating series, and you can show that b sub n, the part that does not alternate, is decreasing. This is what the first condition is, that it's a decreasing series. If you can show it's decreasing, and also that the limit as n goes to infinity of b sub n equals to 0, then the series is convergent. We can say it converges. If it doesn't meet those conditions, we can use the divergence test to prove that it's divergent. So let's look at example 1. Determine whether the series converges or diverges, and they give us this. So the first thing we're going to do is say, well, this, and recognize this is what I just wrote up there. This describes the alternating harmonic series. So we know the regular harmonic diverges. What about alternating? What does it do? So if we're going to apply the alternating series test, you basically want to concentrate on the part that's not alternating. So we will consider just the b sub n part, which is equal to 1 over n. Okay. So what are these conditions? Is this decreasing? Well, I just wrote out some terms, right? 1, 1/2, 1/3, 1/4, and these are being added, right? But the terms, they are decreasing. We can see that. You could do, and later in this video I will do, where we take the derivative and show that something's decreasing. But we can obviously see this is decreasing, so it meets the decreasing condition, okay? And then the second one, how about the limit as n goes to infinity of b sub n, 1 over n? Well, n's going to infinity, so this is definitely going to 0. So it meets both conditions for the alternating series test. So we can say, therefore, this series is convergent, or converges, by the alternating series test, just like that. All right, so let's look at example 2. What's happening here? Well, in example 2, it says determine whether the series converges or diverges. So let's see if we can apply the alternating series test. This -1 to the n plus 1, this is the alternating part. So if we kind of don't worry about that part and just concentrate on b sub n, which is n cubed over the square root of n to the 5th plus n. Let's see, what's happening here? Well, let's see if it's, let's take the limit. Let's do condition 2. Let's take the limit as n goes to infinity of n cubed over the square root of n to the 5th plus n. So one way of handling something like this is limits at infinity is to, when you have a ratio like this, a rational function, you can divide the numerator and the denominator by the highest power of n. Also, L'Hopital's rule would apply, but this one's kind of easier. So if I divide the numerator by n cubed and the denominator by n cubed, when it goes under the square root, this is going to become n to the 6th. So what's happening in the numerator is we get a 1. In the denominator, this is 0 and this is 0. We're basically dividing by 0. So this limit's going to infinity. Well, that does not meet the conditions for the alternating series test, but it does meet the conditions for the test for divergence that we learned at the beginning of all of this series talk. The test for divergence is if you take the limit as n goes to infinity of the a sub n of the term, the nth term, so b sub n would be this. If it does not equal to 0, then it's a divergent series. So this is alternating, right? But so it's gonna, but since it's not going to 0, then it's getting further and further apart when it's going to something like infinity. So this diverges by the test for divergence. All right, let's look at example 3, which says determine whether its series converges or divergent. So this is alternating series. So again, if we take this alternating part and sort of dismiss it, and we just, for the moment, and we look at b sub n, which is the square root of n over n minus 3. Okay, is this decreasing? What I want to do, this time I think I would like to take the derivative. So we'll consider the function f of x, which is the square root of x over x minus 3. So f prime of x would be low, x minus 3, d high, 1/2 x to the negative 1/2, minus high, square root of x, d low, which is just 1 over low, x minus 3 squared. Okay, what's happening here? Well, this is going to be, if I look at, this is x minus 3 over 2 times the square root of x minus the square root of x over x minus 3 squared. I'm going to multiply the numerator and the denominator by the square root of x to kind of clean up my numerator right here. This will distribute here as well as here. 2 over the square root of x times the square root of x. These guys will cancel. So we end up with, oh, and you know what? I'm going to multiply by 2 square root of x. That will make it even cleaner. If I multiply by 2 times the square root of x, then first that will completely kill my fraction, which is nice, and I just end up with x minus 3. Minus the square root of x times 2 square root of x is going to be 2x. In the denominator, I have 2 times the square root of x times x minus 3 squared. All right, this becomes x minus 2x, or negative x minus 3 over 2 times the square root of x times x minus 3 squared. If I look at this, this is a series that starts at 1, so the values are going to be from 1 to infinity. So if I put in 1, this is going to be a negative number in the numerator all the time. In the denominator, these are going to be positive numbers all the time. So this is always negative. So what we found out that was f prime of x is less than 0 all the time, or for values of x that are greater than 1, and that, so if this is negative, then f of x is decreasing. So that's the decreasing part. Now let's look at the second condition. The limit as n goes to infinity of the square root of n over n minus 3. We can use L'Hopital's rule, or we can do the thing where we divide the numerator and denominator by the highest power of n, which is n. So dividing by n is the same thing as multiplying by 1 over n. So this would look like the limit, as n goes to infinity, of the square root of n over n squared. When it goes underneath the square root, it doubles the power. And this would look like n over n minus 3 over n. Okay. The numerator, the square root of n over n squared, is really the square root of 1 over n, and this is going to 0 when n is getting very large. The denominator is going to be, this is going to be 1 minus 0. So basically we have a 0 over 1, which is 0. So we find that the limit as n goes to infinity of b sub n is 0. That's the second condition. It was decreasing. So we can say this guy converges by the alternating series test. Okay, lastly, let's look at example 4. This guy is the alternating part, so we're going to dismiss him for a moment, and we'll concentrate on the part that's not alternating. So b sub n in this case is arctan, or tangent inverse of n. That's what b sub n is. So the limit as n goes to infinity of b sub n in this case would be the limit as n goes to infinity of the tangent inverse of n. But we've looked at this in earlier videos and earlier discussions, and we know that when n goes to infinity, this is tangent inverse, this is headed up to the value of pi over 2. We know this heads to pi over 2, which does not equal 0. So by the test for divergence, this series will diverge. I can't spell diverge. Oh, I'm done. Okay, diverge right there. Okay, that's the alternating series test.